Hi everyone. Welcome to our live stream about bridging comfort and energy efficiency. We are so excited that you decided to join us. My name is Klara and I will be a host today, and together with me it's Stanley. We are both tuning in from Slovenia, just a little bit different parts of the city, but I know you're joining us from all over the globe. So just to start this live stream a little bit more active, and to test the chat box, just let us know where you're coming from. We would love to see how far this live stream is actually reaching. Shortly about myself, as I said, my name is Klara. I've been working in Danfoss for the last, let's say, 9 years, and my experience is mostly from or as a product manager, both for valves and actuators for district energy and for buildings. But today I'm here in the role of a host as a coordinator. So I'm here to basically pose all the challenging and demanding questions to Stanley, basically the ones that you will be preparing and writing in the chat box. And as I said, with me is expert on this topic, so it's Stanley. So Stanley, a short intro about yourself.
Hi, thanks, Klara. Yeah, I'm Stanley. I've been with Danfoss for almost 25 years. I spent most of my time as a business development guy, so I was traveling all over the world, showing or selling our products, and also learning about different applications everywhere. Yeah, so today I'm here to give you a presentation. However, it's also clear that the presentation is not the point. It's about interaction. So if you have questions, feel free to type them in the chat box, and then Klara will give the questions to me, and then I will try to answer. Obviously, I'm subject expert, but I'm not the all-knowing Oracle of Delphi. So some questions might be too difficult even for me. But let's see how far we get, and yeah. Let's have a good discussion on how to create better installations.
Yeah. So actually, what we would like to discuss today is, we know that precise control of the room temperatures is sometimes considered, let's say, as a luxury. For these reasons, spending additional money on modulating actuators or good PICV pressure-independent control valves is seen by some as unnecessary. So we would like to discuss this a little bit more. We will actually discuss what comfort is, in fact, not a luxury, but what, as we see it, as a crucial part of the global drive for the energy efficiency. And this is just a general topic. And as Stanley said, today is all about you. So the purpose is not that we tell you what we know about this topic, but that you actually ask questions that you're interested in. And we will guide the discussion into this direction. So it's an interactive live stream. Use the comments, use the chat box, use the likes. We would love to hear as much from you as possible. But just to warm us up a little bit, Stanley has actually prepared an intro presentation. So I will just give the word to Stanley to kick off.
All right, thanks. I think one of the things that we've seen is now that energy is the prices are actually going through the roof. Is that we see that governments are active now, and they want to really save the energy. And what I know from Europe is that there are a number of countries that actually are now putting limitations on public and also sometimes commercial buildings. So they say, if you are a public building, let's say Italy, Spain, and Greece, for example, you cannot set your air conditioning below 27 degrees. And for the heating, I mean, similar story. Ireland, Belgium, Hungary, and Germany are saying, you can set it above 19 in certain situations. So we can say obviously that you will save energy by doing this because you need to heat and cool less, and also your transfer losses through the walls will also be smaller because the temperature difference between outside and inside will be smaller. So yeah, you will save energy. However, I think that in most cases 19 degrees for many people in winter is too cold, and 27 for many people in summer will be too warm. So what I want to do today is also talk about, let's say, can we maybe do something here without actually compromising the comfort of people. So, and then we had a question, I think, that maybe you can share.
Yeah. So what we will use in this live stream presentation is also a Slido questions, because we would like to actually hear from you as much as possible. So we have a question, if you think it's justified for governments to prescribe what you can set your room temperature to. And I would really advise you to use this Slido so we can use this as a base for discussion later on.
So you can either use the QR code if you are on your laptop and scan it, or you can use the link in the chat to go there. And if you can answer the question, that would be really nice. So basically, what we want to know is kind of like, how do you feel about governments prescribing kind of like, I would say, pretty private things in a way, right? I mean, you're in a room and you are kind of you want to be comfortable when you work, right? Or when you are shopping, or when you are trying to get a new passport or something. And yeah, government is now trying to say, okay, this is what we want to do, and we don't really care much about your comfort. So I guess maybe by the way of how I was framing it, that now people are saying, no, I don't think that government should get involved in this. So yeah, that's so no more answers forthcoming. So yeah, it seems that basically we have a kind of a majority that says, well, I wouldn't like government to decide for me when I'm comfortable. And then, I mean, this is also kind of a logical thing, if we can go back to the presentation maybe, is that the comfort is also a pretty private thing. So for everybody it's different, but also we can even say that it depends on what your current state is. I mean, maybe you are you just woke up and you feel a bit cold because you just got out of your warm bed, or you just had a coffee and you feel warm, or you just came from outside and and outside is cold and now you're hot, or the other way around. So we can also see that your comfort level will change quite a lot during the day. And like I said, I mean, maybe also for therefore it's difficult also to say what is a good temperature for a certain, because it will vary through the day. And then now also we are going immediately into temperature control precision, right? Because you can see that if you have a set point that is somehow in the middle of the zone where you are somehow most of the time comfortable, but your room temperature is actually fluctuating a lot around this set point, then it means that at certain times, even though your control maybe says 22 or 23, which is a temperature that you normally like, you will still feel cold or hot at certain times. So there will be people will complain because the set point is not maintained. And it's also very difficult to then find the right temperature. So that means basically if people are either hot or cold, they either start to mess with the room thermostat. So they try to change it, and it could change quite a few times maybe per day, or they start to complain. And if they say, okay, I'm hot now, what you do, and blah blah blah. So that's also costs, right? I mean, if you're a building owner and you own an office or even another shopping mall maybe, and people start to complain that it's hot or cold, then you need to do something. So it's cost. So what now happens if you basically have a very precise control, like we see here, then you see actually that the sensitivity to the temperature is also much smaller, because we can increase the set point from here to here without actually making people feel uncomfortable. And that is a really important to understand, is that when we are making better controls, we can also have higher efficiency in the controls. And we know that, let's say, if we talk about at cooling, let's say 1 degree of increase in the temperature can be 10 to 15% of energy saving on a yearly basis. For heating, it's 6 to 10%, more or less. So so that is important to realize that when we're talking about, modulating control and putting all this fancy building automation inside, it's not about just making it more fancy. It's also about actually giving tangible benefits, which also translate into actual money. So if you think you save energy by using a cheap control valve with on-off wax actuator, for example, then actually it costs money. So yeah.
We have a first question, maybe connected more to what we were discussing a little bit before, but it's a question coming from William. Will there be a global set point standard to control energy efficiency?
Well, I think that, if we can't even align on let's say the most basic things, it's more a political question, I guess. That then I don't see it happening. However, obviously in most countries there are standards, right? If you so there is also a standard defined sometimes by the principal, by the guy that is financing the building, or sometimes it's also local standards where they say, okay, if the temperature outside is X, in Netherlands I think we use 30 or 35, I'm not even sure, then inside I should be able to reach temperature Y, so 22 most of the time. And with minus temperature is the same. At minus 15 I need to be able to reach 21 inside. So those standards exist, and also they are the basics of like designing the systems, because we have to basically find out how much power we need to put in this building. How big does the chiller need to be? How big does the boiler need to be, if we're talking about heating? And that is based on that calculation. However, it's also important to notice here that this also gives usually extreme temperatures, and that means that your system is also very oversized for quote unquote normal conditions. So if you size it for 35 but now outside it's 25, yeah, you still need to cool, but you don't need to use the full power of your installation. And this is also why this whole control thing is extremely important, because let's say controlling on full load is actually not difficult, because you will just open everything and it's full load. However, going to partial loads where outside conditions are not so extreme, this is actually where it is also where the difficulties in the control actually start to appear. And the lower your load, usually the higher your problems to control properly, because that your valve is almost closed. You have very small movements in the actuator, and also small changes in the actuator can have big effects. So yeah, I don't see a global standard happening. There's also very different ways as to how we look towards air conditioning. I think that specifically cooling, I think that what's acceptable in US would most of the time not be acceptable in Europe, for example, and the other way around. So But there is definitely a standard that is tend to be used for designing, and maybe it is possible that the design associations come together and say, okay, we will change those standards. But I would find it hard to believe that we would do this on a global level. I would say national is already something.
Good. And then, Stanley, another question is, what would you define as an optimum temperature setting?
Well, if there is such a thing, I think the next slide will kind of give you a bit better insight maybe as to how that works. So this very complicated looking graph is made by some American researchers that basically collected a lot of data from a lot of buildings, and they came up with this graph where we see that let's see, where's my cursor here? So this axis is basically the complaint cost. So and 0.1 means that if I spent $1,000 on energy generation or cooling or heating or whatever it is, I will spend $100 on solving complaints. So maybe 10%, or not maybe, exactly 10% of the cost of the energy cost for running the installation will go towards complaint cost. Then here we have the setting of the temperature in Celsius and here in Fahrenheit, because obviously it was American research, but you can pick here. So then and now the smart bit is actually these curved lines that we see here, and these curved lines represent control stability. So if we have that line that is the highest, then this is basically really bad control with a lot of fluctuations. So more or less the fluctuation will be 4 Fahrenheit, which is I think like 2.5 degrees or something. So that's really bad control. And then the lower you get with the lines, the more stable the control is. So now if we talk about ideal temperatures, I think that basically we can say maybe it doesn't exist because I mean, as long as as you stay somewhere here, you will not get so let's say in this region, basically there will not be a lot of change in the complaint rate. So more or less you can also put your temperature setting here, and then and your stability, and then so that's like half a Fahrenheit higher, and you will still be okay. However, as soon as you start to cross one of the lines, basically you're starting to increase costs somehow, because you will increase more, or you will get more complaints until and unless you increase the temperature stability. So if you want to set it to, let's say, let's say 78, and you don't actually make your temperature much more stable, you will actually see that your complaint cost will go up, because your complaint cost follows these lines. So so the point of this graph is basically that your cost of complaint, and we can maybe also translate the complaint as comfort, right? Because if people are comfortable, they're not complaining. So your comfort will not change a lot if you can are able to keep the temperature stable. But if you are having a very unstable temperature, then your cost will go up, and that means also discomfort is going up. So maybe you could, let's say, if this is 23.5, this point here, which is kind of the most or the easiest point to do, then you can probably go up to 25.5 without significantly decreasing comfort. But you better make sure that your control is very, very good. So I hope that this was kind of clear. I mean, if somebody has a question about it, then feel free to ask. But
I'm sure they will come, but no questions on this topic for now.
All right. Okay. So, but essentially, this is the key point. I mean, we were talking that, you know, in Italy, you are not supposed to put your setting below 27, which is kind of off the chart here, but 26 is feasible as long as you have very precise control. 27 also may be feasible, and one thing is for sure, that if you make sure that your control is very stable, that even if people are maybe not all comfortable at all times at 27, the complaints will be much lower. So, and here is where I mean, this was kind of the title also of the thing, is bridging comfort and energy efficiency, is that comfort actually is directly connected to energy efficiency. Because if people are comfortable by having a stable indoor temperature, then they will complain less, and that means also that you have more space to change temperature settings and to still have them comfortable. I might also add, by the way, which is not included in this graph, but it is included in that study, that the speed of change is also quite important. So if people are, or let's say if the room temperature is fluctuating a lot, and sometimes you have this, like if you have a fan coil unit with a fan that's blowing in your neck or something, and if it changes from cold to warm to cold to warm all the time, this is also when you are going to feel very uncomfortable. So all of this is to say, you need to have precise control, and for sure you also need to be able to modulate. So ideally you would find a spot in the control where you basically just nothing changes anymore, and where you are just keeping the same temperature at all times, except when there is like a disturbance, so sun starts to shine in the room or something, whatever. But all right, I see that my camera is doing a bit weird. Everybody else is seeing this.
Yeah, you're breaking off, Stanley, a little bit. Since we lost Stanley just for a second, hope he will be able to join back very fast.
Yes, we're still good.
Yeah.
Oh,
We have a little bit of technical problems, but I think we'll be back on track in a second.
All right. Good.
Okay.
Yeah. I think everything is fine now, right? So so we can continue.
So we have some time, Stanley, since you stopped talking finally. So people were actually able to ask some questions. So we have a question from Felipe. How basically graph can be interpreted by using different types of control actuators?
Well, that is actually, if you I could say, I mean, the different type of actuators is one thing, but it's about the performance of the valve and the actuator together. However, it's pretty clear that if you are in this pink or what is it, cyan kind of like graph, that this is probably you know, a control valve with on-off control, because that is and I have some graph that I can show actually what the difference is. But so I would say that the lower the line is, so the better the control is. So usually the better the control valve and the better the actuator is. And you know, on-off and modulation are, let's say, two extremes here, or let's say the ones that are the biggest difference. But I would say this one is kind of like on-off, and the further you go, definitely at some point you need to start modulating here, and also you need to start thinking about, you know, proper sizing and proper and proper pressure independence, which we will touch later. I hope that was an answer to the question. Is there hi Felipe, by the way. Nice to see you.
And we have also a question from Andre, and he's asking what kind of controller would you recommend for global use in air conditioning? If you're able to answer that, Stanley.
Yeah, it's a quite wide question, I would say, but generally, and this is also where we are. I mean, obviously, we have to look at the whole control loop, right? And the loop has a valve, an actuator, and some kind of thermostat or some kind of controller. And you know what we see now, and that's also the trend. First of all, I think that we are seeing that we need to go to pressure independent control valves, and I will tell a bit more on that later, because that and that is also how most these new designs are coming out. Although there is also quite large regional differences here, is where sometimes, you know, in some countries everybody's using pressure independent control valves, and in other countries they're a bit slower. And obviously you need to modulate. There's no that's at least the one thing that I can say. So you need to have an actuator that is 0 to 10 volt or 2 to 20 milliamps if that's your preference, but you need to be able to have more positions on your valve than just open or closed. And then the controller, yeah, I mean, also here, I mean, you know, it's, you need to have either, you know, connected controllers that can use the good feedback signals and be able to have precise control. But also, if we're talking about the controls, you need to sometimes use the right parameters to actually do that. So P-band, integration time, and sometimes even differentiation need to be properly set. But that's, I would say, a 3-hour presentation, which I don't think that we have time for now. But yeah, I mean, if you ask me straightforward, then I'm mostly a valves expert. I would say pressure independent control valves and modulating actuators. That's it. And then a good thermostat or controller.
Good, thanks, Stanley. No more questions for now, so we can move on.
Right. So we can also say that you know, it has an impact on comfort, but it also has an impact on how the system works as in general. So I mean, there's a lot of text on the slide, but I think that basically the main part of this is that if you have no proper controls, improper controls, and you have a lot of interference, then your chiller is always, and also your boiler, by the way, is always following the real demand. So you have a real demand, but your chiller is only at this real demand half an hour after the fact, by which time maybe the demand already changed. So that means that by having all these fluctuations in the system, your chiller and boiler are always, you know, changing loads. And that is actually also really inefficient way to work, specifically for chillers. I mean, if they have to switch on or off compressors, there is additional energy cost that that they need to consume. So the COP will go down, and while actually, you know, there's no reason to it, but it's just because your chiller is always trying to find the right position to actually produce, but because you have the fluctuations, it's never exactly right.
Stanley, a question is why do actually these fluctuations occur in the system, the pressure fluctuations?
Yeah, so one of the things that, and this is again why we're really, you know, recommending pressure independent control, is because the if you have, let's say, normal two-way valves that are not pressure independent, and some valve closes, then basically the flows in the system shift. And that means if one valve closes, that some of the other flows in the system will go up. And that means that if you are, let's say there's two rooms next to each other, and one of them is operating on 50% and is now going to 20%, and the room next door was operating on 50%, but now actually gets 60 or 70, then basically you will be impacting the room temperature here, and your control needs to react to that. So what you will see is that first of all, you see a shift, because then there's basically more capacity put into this room than actually needed, but it is consumed. And then the room thermostat will bring it back. But in the meantime, the chiller has tried to compensate for this additional capacity. So, and this is why you have these fluctuations. It's because the valves have interference.
Good, thank you.
So I guess that was the question. Any more questions right now?
No, for now, no.
All right, then let me see. So then we bring then to that kind of the conclusion, what we need. So, and as I was saying in the beginning, I mean, on full load, it's not so difficult to control the system, or basically you're not controlling it. It's just like, you know, if you're in the car and you just put your foot down, yeah, you know, the car will speed up and, you know, you will have full power. However, if you if you need lower speeds, then you know, you need to control the throttle. And I mean, most people would recognize this. Or I mean, if you have a very powerful car and you need to drive 30 kilometers per hour or something, this is actually sometimes quite difficult to manage that, because the car just wants to do more, right? It just wants to go faster. So controlling the low capacities, so like say shoulder seasons in spring and autumn, where demand is really not high but it's still there, this is actually where temperature fluctuations will be most prominent. Although if you are designing or if the system is not well designed, then you can have it basically almost on any in any season, because I mean, first of all, you need to make sure that there's no interdependence, so that the valves don't influence each other too much. So that means that either you will have pressure independent control, or you will have a very high authority on the valve, which basically means that it has a lot of resistance. I mean, the authority is, again, I would say a topic in itself. It's quite, but more or less we can say the higher the resistance of the valve, so the lower the kV value, the better the authority. And you know, but also if you have a very small valve that has a very high authority and therefore a very good control stability, then also you have very high pumping cost, because this resistance needs also to be covered by the pump, right? So that is that's kind of like a balance you need to find. So, and that will give you then, those two things will give you a very precise modulation and pressure independence. So there is all these things are needed to get the stable control.
Stanley, I know that you already briefly described what valve authority is, and you said that you can have a full presentation on this topic, but still maybe for Roger to just elaborate a little bit more.
Yeah, so the official definition is the ability of the control valve to impose its characteristic on the system. So I'm sure now everybody understands exactly what authority is. However, for the kids in the back, so the authority basically tells you how close the real performance of the valve in that particular system is to its specified characteristic. So, for example, if you have a linear valve, which is then the easiest to explain without additional pictures, when it is 50% open, it's supposed to be also allowing 50% of the flow. When it's 75% open, it's also allowing for 75. It should also give you 75% of the flow. 100% open, 100% of the flow. That is what supposedly is the characteristic that's in your data sheet of the valve. Now, in because the pressure, as I was explaining, changes in the system. So if I'm closing the valve, basically I'm getting more pressure available. So that means that essentially when I have the valve 50% open, I don't get 50% of the flow, but I get maybe 70% of the flow. And an authority of 1, which is the highest that you can get, means I follow exactly the characteristic that that is in the data sheet. And the lower the authority gets, the more you deviate from that ideal. And let's say the lower the characteristic, I mean, this is linear, and then you go basically like that. So so that is kind of how authority is. But I mean, it's also okay if it's not clear yet, because it's like I said, it's pretty complicated topic. Then it's also fine to reach out in the chat, and then we will ask, because I can also send maybe some additional material that you can
exactly. And we will probably not be able to answer all of the questions, in live stream. So you can always also contact us directly via LinkedIn, and we will try to clarify, whatever is not
all
clear
right.
still.
So then, and because I've been mentioning pressure independent control quite a lot. So this is a pressure independent control valve. And here we have two parts actually in the control valve. This is the top part here is a normal control valve, which can open and close, and works like any other two-way valve. However, the smart bit is here in the bottom, is where we have a pressure controller. And the pressure controller keeps the constant differential pressure across the control valve. And now, basically, if you kind of follow my explanation on authority, now you can also see why this is important, actually, because it automatically gives you actually an authority of 1. Because the pressure on your control valve is always the same, so I have no changes in my characteristic. Because at 50% closed, my pressure is exactly the same as at 100% closed. So at 50% opening, I will have 50% of the flow. So you have a high authority always, a predictable control characteristic, and that means that you always know what your flow is going to be. And we were discussing also interdependencies before, is like, if valves open and close, this valve doesn't care, because the pressure controller will keep the fluctuations in the system under control, and basically make sure that there is no interdependency, and it does not it does not react to other valves. So you will have stable control, precise control, and no interdependencies.
Okay,
so,
we have one question. It's can you have pressure independent control with pressure controllers?
Partially, yes. Because if I was, I mean, I know this also in certain parts of the world, this is still quite often used. So what you do is you put on the branch, you put a pressure controller that keeps a stable differential pressure control, and then on the, let's say, on the terminal units on this branch, you will put balancing valves to make sure that you have the proper distribution here. So now, that is essentially not a bad solution. However, first of all, it has two kind of small problems. Is that one of them is that that you still need to do balancing on the branches. So you need to actually take some measuring equipment out and go to each valve to measure them and set them. For pressure independent control valve, this is not really needed because you can basically just set them to the right flow. And also there is a certain authority issue because the valves will still influence each other when they start to open and close to a certain extent. However, it's obviously much better than not having any pressure control at all. But I think also with the last, let's say, developments when we talk about pricing, competition, and all those things, I think that doing that, so putting the pressure controller on the branch, is actually more expensive than using PICVs on each and every terminal unit. So essentially, the pressure independent control has a pressure controller on each valve, which will give you, let's say, a few benefits like precise control and less commissioning because there's no measuring and no internal balancing. And as far as the price difference is that also not really an issue anymore. So we could say that that for certain applications, pressure controllers like radiators that are kind of or sometimes also based around this design, it's okay. But for most situations, pressure independence control is actually a better solution and also most of the time cheaper. It depends a bit on the size of your branch where the, let's say, the crossover point is, but generally speaking, we can say that PICV is a cheaper solution actually as far as investment goes. So why wouldn't you choose the better solution if it's not more expensive? Why wouldn't you choose that one? Right.
Good, Stanley.
No more questions, I'm assuming. So just also to give you a bit of an idea as to what this means. So we can see here, this is actually done in an actual test room that we have here on the university in Slovenia, Ljubljana. And you can see the set point in green. And the first part is basically motorized control valve with on-off actuators. And you see, first of all, you see a lot of fluctuations here. And we could say also this is not even a complicated system, right? So this is a system that operates on one valve. So there's not even interference from other other valves. This is just how it operates. And you can see that the room temperature is already fluctuating basically almost 2 degrees. And also important to see here is that the water quantity, this is the gray line here, is also fluctuating a lot. And that means that basically your pump is constantly adjusting and high flow, low flow, high flow, low flow. And if you're cooling, your chiller is also constantly trying to find the right operating point. And then here at this point, we're switching over to pressure independent control. You can see that immediately there's temperature stability, and here we introduced some disturbances in the room. So basically, we switched on some load in the room, and then you can see that it's trying to find the point, and then more or less the flow drops because the load on the room is higher, and then basically from here we have already stable control, and here it's a bit of an overshoot, but that's also how control works, because we were also discussing before like what's a good controller. I mean, this is based on only P-band controller, and then you see that you have this overshoot. If you have integration and also differentiation, again, complete new topic and big topic, then you could maybe also control this away. But stable flows all the way and stable temperatures.
Stanley, just I would like to have a comment. I think we received a really nice comment in the chat box from Pedro saying how good Danfoss products are. Basically, he's saying that the room temperature must be set according to the circumstances and depends on the building's fabric and weather conditions. Their products offer a good way to regulate this. I have Danfoss products and they are good. Greetings to Danfoss team, Pedro. So thank you, Pedro, for that. It's a nice comment that we received.
Yeah.
Good. And then we have a new question from Niels, who is actually asking how small are the flows that you can control with PICV?
Yeah, I would say that is a bit dependent on a few factors. I would say the size of the valve. I would say that the flow is higher on the if you have bigger valves, and also on the accuracy of the actuator. However, we have demo panels, and we test a lot on our valves, because this is also we want to understand our own product basically better than anybody else. And we know that, for example, on the DN15, it's very possible for us to control 5 liters per hour. So, I mean, if you want to understand how big that flow is, then it means that during an hour, if you put a bucket behind it, it will fill the bucket for half, because usually buckets are 10 liters, right? So you can understand that this is a really tiny flow, and that is definitely also part of the benefits that pressure controller brings, right? It's because we have the same pressure across the control valve. We also have a very precise control also on the lower limits, and that means that if you are talking about shoulder seasons with very low loads, and also what we see now in West Europe mostly is lots of radiant panels in the ceilings, which is a very good system, but generally speaking also have very small flows, even as a maximum flow, like, I don't know, 40-50 liters per hour. Then it is also very important to be able to control these small flows, and this is again very important for pressure independence. So I think we're coming to the end. I mean, also, if you remember the vicious circle where we were talking about chiller not being able to find the right operating point, if you have pressure independent control, then you are much more able to find the right operating point with the chiller, because one valve changing in the whole system probably doesn't have that much impact. However, if it impacts everything else, it becomes a problem. But now the valves will be very much stable, because they will control only based on the actual load in the system, and that means your chiller will be operating at a much better point. And also, as you can see maybe from this one here, this is a system before, where you see that they designed for an 8K delta T, and it was actually 3 degrees, and also a lot of variation here as to what is the return temperature, and the supply temperature is also fluctuating a lot. And then more or less they changed the system, and they did nothing else except change the control valves that were there to pressure independent control valves, so ABQMs. And what happened is basically suddenly, night and day, we have a very nice delta T, which is increasing your chiller lift a lot. So also your COP will go up a lot. Also, again, no time to go into that topic, is also again half hour the presentation, but trust me, having a high delta T is great for your chiller. And I think most of the guys will remember, if they're working with chillers at all, low delta T syndrome. This is definitely what could happen here a lot. Here, probably not ever. And you know, your supply and return temperature are much more stable. And if you see what is the efficiency of the system, basically, it's you save 60% on pumping energy, which is the second biggest consumer in the system. I mean, the chiller is the biggest, obviously, but after that, it's the pump. You can save a lot of energy on there, and overall, your system will just function that much better. And this is where we are talking, you know, when we're also bringing together the whole thing again, you know, the comfort that we bring in the room can actually, on the whole chain in the system, bring you additional comfort and also additional savings. Sorry, so you will be able to save energy over the whole chain. So I guess then.
Stanley, just to jump in, we have a question from Noah.
Yeah.
What is the influence of delta T on chiller efficiency?
Yeah, I mean, essentially, we can say that the delta T will improve your chiller lift, and so yeah, it's a quite a big topic also to go into, but it will improve the COP of your chiller because you don't need to change the water temperature as much, or let's say the difference between condenser and evaporator is smaller, and therefore it is more efficient. I mean, without additional slides, I'm afraid I can't explain it much more. But I mean, we had also a lot of discussions, even with chiller producers, on this topic, because generally speaking, the software that chiller producers supply does not account for this really, because they kind of assume that if you design for 8 degrees delta T, it will be there. And if you design your system properly, so as you saw before with pressure independent control valves, it is probably there. But I mean, I was also a commissioning engineer, and you know, if you go to an average building, specifically if it's like maybe 10, 15 years old, and you go to the technical room and you look at what the delta T is on the system, it can be anything from 1 to 2 to 4 degrees maybe, but definitely, or it's very seldomly actually what is designed. So and again, the COP will or it has a direct influence on the COP of the chiller.
Good, thanks, Andy. We don't have any additional questions for now.
All right, then. Okay, we're pretty much on time. So to summarize, I mean, yeah, obviously changing the temperature in your system or your room temperature can lead to savings. But if you do not want to have, if you don't want to have additional complaints from people in the buildings, then you also need to make sure that you have the room temperature also under control. And generally speaking, it's you need to have a properly designed control valve with modulation and proper controller. And generally speaking, I think that nowadays current wisdom is saying pressure independent control valves is the best way to go. So I think.
Good. Thank you, Stanley, for summing up. I think it was a very interesting and a very relevant topic. Since we don't have any more questions from the public, we actually have questions for you. And the team in the back will now post a new slider question. And we are really interested, you know, to hear in what role are you working on in the HVAC industry? Are you from sales, designer, contractor, producer, or you don't work in this industry at all, or you work in some other position? Because we would like to see who actually joined this live stream, so we can maybe next time also target a little bit more with the topic. So if you can again use this slide or to provide some answers, we would be very happy.
And then as a closer, also after this one, there will also be a question where we actually are asking you for topics that we maybe want to that you maybe want us to cover in the future. So if you say, okay, I mean, I would really like Danfoss to explain to me this or that, and maybe it doesn't really need to be a very big topic. I mean, if it's a small question or small thing that I need to cover, we can maybe put it just as a kind of a question answer session in the next live stream. But that would also be interesting for us if you would be so kind as to answer those questions. And then, yeah, I think that's it for me. I hope you enjoyed it. I hope you learned something.
Yeah, and really, Stanley, thank you for sharing your knowledge with us. I think it was very insightful and again, a very relevant topic. For everybody who posts some questions and it got lost during all the comments, we will, after the live stream is finished, we will go through and try to answer you person to person. But if we have missed someone, then of course you can also contact us directly. We're happy to answer any question that you have. And yeah, this video will be available later on LinkedIn. And we are right now live streaming also on Facebook and YouTube. So you can always rewatch if you have missed it, or if some colleagues you think would be interested into the topic. So thank you again for joining. It was yeah, it was a very nice live session.
So thank you, and please don't forget to answer the questions. See you next time, maybe.
Yeah, thank you. Bye.